Hello everyone and thank you for joining us today. Welcome to Megger's special webinar series. Today's topic is cable fault location with Megger Smart Thump and Digiphone. My name is Michael Fleischer and I'm the digital marketing specialist for Megger. I'll be acting as the moderator for today's presentation and supporting you on any technical issues or questions for our presenter. On the right side of your screen, you'll see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment at the end of the webinar. Our presenter today is Marshall Bird, Regional Sales Manager. Also to assist with the question and answer session, we have three panelists joining us today. Henning Ochen, Product Manager, Robert Probst, Product Manager, and Sergio Razzo, Cable Area Sales Manager. All right, let's go ahead and get started. Thanks for joining us today, Marshall.
Good morning, everybody. Welcome to the webinar. Today, the webinar will cover these topics. We'll start with a basic overview of cable fault location. We'll talk a little bit about the Megger Smart Thump. Then we'll move into fault location in 3 easy steps using the Megger Thump 25. We'll talk about pinpointing difficult faults with the Digiphone. We'll work a little bit on how you verify whether you did or did not find the fault distance. And we'll wrap up with a little bit of Megger fault location products and common accessories, followed by the question and answer session. So let's start with just a real general overview of cable fault location. We'll talk a little bit about different cable types, cable insulation and construction, fault types, and a very basic process or sequence for fault locating on a single-phase direct buried cable. So let's look at cable types. With low voltage cables, sub-primary cables, of course each of these have their different voltage ranges. Primary cable, medium voltage. This is where today's webinar is going to focus at. Of course, you have higher voltage sub-transmission and transmission cables. So insulation types. There's basically 2 types of insulation, extruded or laminated. The laminated might be a PILC, a paper lead insulated cable. The extruded plastic insulated cable, EPR or XLPE, that will be the type of insulation that we'll basically be talking about today. Before we get too deep into it, when people talk about fault locating, sometimes they're thinking about this, fault locating on a secondary cable. In the United States, triplex is quite common. 2 insulated hot legs, 1 insulated neutral, and we use a completely different method of fault locating for this type of cable than what we're going to talk about today. Generally for secondary, we would use a voltage gradient method. And this is an unshielded cable, and so this really isn't part of today's webinar. What we're going to be focusing on more is shielded cables, and the construction could be of different types. 3-phase might be common. The single-phase shielded medium voltage cable, this is what we're going to be focusing on in today's webinar, and the arc reflection technique works well on these type of cables. It will work on the 3 core cables also, but the focus will be this type of cable, and it's common to see the cable class for this medium voltage of 15, 25, or 35 kV class cable. And the key point about it is this is a shielded cable, usually with a neutral concentric, and the arc reflection method that we're going to be reviewing works well on this type of cable. So some common fault types. In very basic terms, we could have a pinhole fault, an open conductor, or a shorted conductor. And again, in very basic terms, we can break these apart into high resistance faults or low resistance faults. If we dive in just a little bit on the pinhole fault, this is a very common way that a medium voltage cable can fail. especially older cables. Here you can see why we call it a pinhole. It's just a hole in the insulation itself, and that allows the voltage to flash over from the center conductor out to the shield or neutral concentric. Typically, this is a very high resistive fault, over 1,000 ohms. What that means is it typically takes quite a bit of voltage to break it over. 4 to 8 kV would be very common flashover voltage for 15 cable, and probably also would be a common flashover voltage for 25 and even 35 kV class cables if it has a nice carbon path. There's an example of a pinhole underneath a pothead. And one thing to note, a pinhole fault, the center conductor is continuous, but not in contact with the neutral concentric. Another fairly common type of fault would be an open conductor. This is where the fault current has burned the center conductor clear in half, or perhaps it was burnt in half because during the sectionalizing process, maybe they reclosed on it several times, so the fault saw fault current numerous times and it burnt it in half. Now the radar cannot see past this fault. It can see up to it, but it can't see past it. And we'll talk about it later, but on the radar signature, it looks just like the end of a cable. And one of the things to note is this type of fault, it may be burned back from the source side, and it may not flash over very good. But on the other hand, it may flash over very easy from the load side. And finally, we have shorted conductor. This is not very common, but this would be an example of where the conductor and the shield, the neutral concentric, are in direct contact with each other. An example of this would be a ground rod or a stop sign that drove right through the cable and shorted the conductors together. It does happen, but it's not very common. If it does happen, it's a low resistance, typically less than 100 ohms. And the radar can see the short, but because there's no gap to flash across, if you connect the thumper and thump on it, it may not produce any noise to hear for pinpointing. Okay, so let's talk just a little bit about the fault locating process. First, we'll talk a little bit about safety. Many times, sectionalizing would be considered part of the fault locating process. Now, we're not going to talk about sectionalizing in this webinar, but that's basically where you're isolating down to a single faulted cable. We're going to focus on the fault locating process for direct buried cable, no branching, not a network system, just a simple point A to point B cable. And for that type of a cable, medium voltage cable, the steps are: first you would trace it so you know where the cable path is in the ground. Then we would do a breakdown test, pre-locate, get our distances, and then thump and pinpoint. And those last three is what this webinar basically will focus on. But first, let's talk just a little bit about safety. Obviously, when you're working with a cable fault locating system out in the field, you're going to follow your company's established safety rules. And that includes some form of making sure the cable is de-energized and grounded before you connect your test set. You want to reduce the risk of backfeed damage to anybody or property. While you're working with a thumper out in the field, there's three sources of hazardous voltage that you need to consider. Obviously, there's operating voltage, and you'll have gone through the appropriate test at dead, ground at dead procedure. Because you're working on a cable, you could have induced voltage from nearby energized cables. You could also, if it was a good cable, you might have residual voltage on the cable from the work you did with your thumper or hypod. In other words, you may have charged up that cable. And then your third source of possible energy is the thumper itself. It is a high voltage device. It has a high voltage DC power supply in it, and one or more capacitors that could be stored, that could hold energy inside of them. So these are the three sources of voltage that you always need to be aware of when you're working with a thumper out in the field. Now, we'll go over this really lightly, but one of the safety processes, of course, is to connect your equipment properly. You're going to have gone through your tested dead, grounded dead procedure. Sequentially, you'll hook the safety ground up to the system ground as shown here by number 1. Second, you would hook up the high voltage return to your neutral concentric. And third, you would hook the high voltage output to the center conductor in some form or fashion. Now, if you notice on this picture, there is a blue dotted line here, and that's to represent that Megger Smart Thump has a safety circuit built into it that requires connection 1 and 2 to be at the same potential. If it's not, if you for some reason don't have one of the grounds connected properly, that circuit will trip and it won't let you go hot. Okay, so that was a brief overview of the process. Let's talk a little bit about the Megger Smart Thump itself. So the new Smart Thump comes in different configurations. Here we see a portable battery-powered unit. It also can come in a truck mount configuration. Here you see it with a control head that's on an umbilical cord where the control head can be mounted separate away from the thumper itself. And all of the Smart Thumps have an integrated TDR, time domain reflectometer, or radar. In addition to the Smart Thump 25, Megger also offers a Smart Thump 16 and a much smaller Easy Thump. And all of these units operate with the same control panel. Basically, if you can run one, you can run the other. So it's just a matter of choosing the appropriate voltage level for what you need at your particular work site. If we focus in just a little bit on the control panel, you know, if we were to go around it, we have emergency off, we have some high voltage on off, electrical power on. But the main thing we're going to focus on is that this unit is driven with a single control knob. I call it a mouse. If you rotate this knob left or right, it's like sliding your mouse left or right. And if you click on it, it provides it's like a right click on a mouse. So using the Smart Thump, let's focus in on the 3 steps for fault locating using the Smart Thump 25. And the Smart Thump has a built-in fault locate sequence. So if we start with the breakdown test, after we've completed the breakdown test, the Smart Thump will pull us through to the locate step to get a distance. And then after we get our distances, the unit will pull us through to the thump step. So it has a built-in sequence that we simply have to follow the instructions on the display. So let's start with step 1, breakdown using a DC high pot. So with that knob right there, when we click on it, on high pot, it will start the sequence. And it would look something like this. First, we would select high pot. We would then adjust left or right and pick the voltage level that we want to do our breakdown test at. And it would ask us permission by pushing the green high voltage on to go hot. And then it would charge the unit up. And I should pause here for just a minute. When I use the term DC high pot or breakdown test, what we're doing is a simple troubleshooting step. We're not doing a acceptance or commissioning test. You could use a DC high pot to do an acceptance test on paper insulated cable. But in today's world, if you're doing that type of testing, an acceptance or maintenance withstand test on solid dielectric cable, generally you would use a VLF test set. You wouldn't use a DC high pot. So we're just using the high pot here to verify whether the cable is or is not faulted. So to get back to the slide, you can see this lower right-hand corner. Right now it's charging up the cable, and at some point the fault is going to flash over, and we'll get a message like this. And said breakdown at 3 kV. And if you notice at the bottom of the screen, it says start fault locating. It's ready with the click of the knob. It's ready to pull us to the next step. But before we do that, let's look at a couple other messages you might get. You could get a message at the end of a breakdown test that says no flashover. And that could indicate that you're on a good cable. It shouldn't happen, but sometimes a cable might be mistagged or something. So the no flashover, it doesn't guarantee that you have a good cable, but it's a strong clue that that your cable's not faulted. You could get a message like this, cable not chargeable. And this could indicate that you have a fault with a very low resistance, perhaps a dead short. Or it could be as simple as somebody left the far end grounded instead of stood off. So there's a short on the cable, but that's because somebody left a ground on the far end. So the Smart Thump 25 can give you additional messages. This webinar is just going to go through the basic process of kind of a 1, 2, 3 type sequence. Now, before we move on, let's circle back and look just a little closer at the breakdown test itself. So here we have the Smart Thump connected to a faulted cable, and when we turn on and charge up the cable, at some point there'll be flashover, and when that happens, the Smart Thump tells us what the breakdown voltage is, and then we're ready to move to the next step. So why do we do a breakdown test? It's valuable for multiple reasons. Some of the key reasons are it verifies we're working a faulted cable, and that means we're not going to accidentally thump on a good cable. You don't want to, thumping on a good cable is not good for it, and it's not good for the thumper. Probably more important, on that faulted cable now, we now know the flashover or breakdown voltage of that specific fault. So we can avoid thumping at too high of a voltage, and we can choose the best voltage range to produce maximum noise at minimum voltage. Okay, so let's move to step 2. Locate, get a distance to the end of the cable and the distance to the fault. This is where we finished at. We did our breakdown test, and down at the bottom, it says start fault locating. We use the single control knob, and it's going to pull us. It won't be exactly this screen, but you can see here the next step is locate. And it would look something like this. First, the unit's going to search for a cable end. Then it's going to ask us to verify the distance that it found, in this case, 940 feet. Then it's going to ask us to start the fault trace. We'll adjust the voltage, and typically at this voltage adjustment, we would go 1 or 2 kV more than the test we just finished, the breakdown. So if it broke down at, say, 8 kV, we might want to do an arc reflection shot at 10 kV. It's going to ask us to go hot, and it's going to charge up to whatever voltage level we did and release a single shot of voltage. And this is where we wind up at. So now we have 2 distances. We have a distance to the far end of the cable, and we have our fault distance. And this is referred to as the arc reflection method. So before we move on to step 3, let's just quickly review, very quickly, how arc reflection method works. So we have our Smart Thump 25 connected to the cable. And as mentioned, the 25 has a Tdr radar built into it. And what's going to happen is the radar is going to send a low voltage pulse down the cable, and it's going to reflect off the far end. And on the display screen, we'll see something like the blue trace above. Now, you notice when we went through that, this is a faulted cable with, you can see the red lightning bolt in the middle indicating there's a pinhole fault. But the radar by itself, that low voltage radar can't see the fault. What we have to do, and before I move on, here's a picture of a real one where you can see the open end at 549. But what we have to do to see the fault is we have to combine high voltage pulse and a low voltage pulse. So the high voltage pulse, the high voltage shot is what I usually refer to it. This is coming from the thumper. We're going to charge up the capacitor. It's going to initiate an arc or flash between the center conductor and neutral concentric. That flash, for a few milliseconds there, that arc, that's an electrical short. And the radar will produce a low voltage pulse, and that low voltage pulse will reflect off of that temporary short, that electrical short that we created with the thumper. So here's kind of how it works. Again, we have our Smart Thump 25 connected to the cable. On the screen, we're seeing that blue reference trace where we have a distance to the far end. We charge up the capacitor to the selected voltage level. We release a single shot. That high voltage goes down the cable and creates an arc, and right behind it, the radar comes and reflects off of that electrical short. And you can see that now with the red trace. The red trace is mirroring the blue trace, and at some point, the red trace V's down, and that's the fault location. And the electronics will calculate the distance to the fault for us. And here's an example of a real one where we have an open end, again, at 549 feet, and we can see the fault at 178 feet. Okay, so step 3, thumping, make noise in the ground. We finish here, have our distances. We have a distance to the end of the cable, and more importantly, we have a fault distance. Now we're ready to go pinpoint that fault. Again, we're going to use the single control knob. It's going to pull us into the thumping function, and it will look something like this. First, we'll set the voltage. And again, we know what the breakdown voltage is, so we know where to set our thumper at. We're not guessing. We can adjust the cycle speed at how fast the thumper cycles. It's going to, again, ask us permission. I should pause here and mention one of the nice safety features of the Smart Thump 25 is it's always asking permission before it goes hot, so that you're not going to be applying voltage except for when you choose to. And then at this point we would be thumping. In this case, the operator selected 8.6 kV to cycle thump at. The unit's going to charge up the capacitor to that voltage level and then cycle. And it's going to continue that process until we stop the thumper. And of course, we're going to stop the thumper after we pinpointed the fault. So at some point, we'll stop it and it will ground everything out. So before we move on, let's talk just a little bit about thumping. Thumping, we want to make a loud noise at the fault. That's the goal, to create a loud noise. And we want to be able to, at the fault location, we want to be able to stand on it and hear and feel that thump. And so the louder it is, the better. And the loudness depends on two things. First, the capacitance that we use. Inside of the thumper is a capacitor. It should be roughly 5 to 10 times greater than the inherent capacitance of the cable. And second, we have voltage. We need to use enough voltage to exceed breakdown of the fault so that we can flash it over. If we combine these two things together, we can get a unit of energy called joules, and joules is directly relates to the loudness of the arc. So more joules equals more noise. More noise means it's easier to pinpoint, to locate the fault. The formula itself is voltage squared times capacitance divided by 2. And what that means is there's two different ways to increase the joules. We can increase the joules by increasing voltage, or we can increase the joules by using more capacitance. The second option is preferred. If we increase the joules by using a larger capacitor, this allows us to make the same or more amount of noise with less voltage stress. So let's look at that just a little bit closer. Here we have represented the voltage ranges of the Smart Thump 25. If we look on the left side of the screen, we have a 12.5 kV range, and that's associated with a large capacitor. If we fill that large capacitor, if we charge it to the maximum of that range, we charge it up to 12.5 kV, it will produce 1600 joules of energy or noise. Now, for some reason, say breakdown was above 12.5 kV, we have no choice but to use the higher voltage range. We have a 25 kV range associated with a smaller capacitor. If we charge that capacitor all the way up to 25 kV, we're once again at 1600 joules of energy. So this particular thumper, the Smart Thump 25, has two maximum noise positions. You could also, not inadvertently, but you don't want to use the high voltage range and only fill it part of the way up. If you do that, you get about 1/4 of the joules of energy. So in this case, if we use that smaller capacitor and we only charged it to 12.5 kV, we would only get 400 joules. Now, one of the nice things about the Smart Thump is if you try to use less than 12.5 kV, it automatically switches to the larger capacitor. So it avoids the problem that you can have with the older style thumpers, where you could put them in the high voltage range and not use enough voltage to make sufficient noise. Let's look a little closer at that. If we take the Smart Thump 25 and we set it at 7 kV, it'll show us in the lower right-hand corner the joules it's going to produce. And in this case, it'd be 502 joules. I really like this display because you can see how many joules you have at whatever voltage level you set. So again, if we take the thumper and we set it to 12.5 kV, it's going to produce 1600 joules. And then if we have to go above 12.5 kV, it's going to switch capacitors on us. In this case, we've set the unit to 14 kV, and it would produce 502 joules. Just kind of a side note, 500 joules is sort of a rule of thumb. If you have 500 joules or more, you probably have sufficient noise in the ground to hear and find the fault. And then finally, again, if we max this unit out, it produces 1600 joules. And the point of these slides is if you can see that at 12.5 kV, we make just as much noise as we do at 25. And so we want the operators to always use the lowest voltage range that they can get away with so that you're making maximum noise at minimum voltage. Okay, so moving on, let's talk about pinpointing faults, difficult faults with the Digiphone. So once the thumper's thumping, generally we just walk out the distance that the radar gave us, and we pinpoint the fault by sound and feel. Usually if we're close to it, we can just walk right to it and we can hear it and feel it thumping in the ground. But that's not always the case. Sometimes, even with a lot of joules, we have what we call a quiet fault. It's not, when you're standing above it, you can't hear or feel it. Also, sometimes the arc reflection method doesn't give us a distance. In that case, we may have to walk the entire cable path. We know the fault is on the cable somewhere, but we could have a 2,000-foot cable and we don't know where the fault is. In cases like this, the Digiphone is invaluable. It's really our friend. It's going to save us time. It's also going to reduce the number of thumps we have to put into that cable. So let's talk a little bit about how the Digiphone works. And it's much more than just a listening device. It's more than an amplified microphone sitting on the ground. So it's going to significantly reduce the duration and number of thumps, help us avoid digging in the wrong spot. It uses what we call the coincidence method. We describe that with lightning and thunder, which is a timing comparison between the electromagnetic pulse and the acoustic wave. The Digiphone triggers off of the first sound, not the loudest sound. So if for some reason you're doing pinpointing in your cables in a conduit, it will still pinpoint it even though you have that echo effect in conduit. The lightning and thunder or coincidence method, let's describe briefly how that works. So here we have a pictorial. We have a faulted cable down in the ground, and up above it, we have the Digiphone sensor sitting on the ground. When we cycle the thumper, there's going to be an electromagnetic field represented by the dotted red line and a sound wave represented by the half moon. And the electromagnetic wave is going to travel very fast. So if we refer back to the lightning and thunder method, the electromagnetic wave is lightning. Now, our eye can see lightning at the speed of light. So let's say off in the distance, there's a storm and a lightning bolt flashes. Your eye sees that lightning at the speed of light. And then there's going to be a amount of time before your ear hears the thunder. And if the lightning was half the distance, your ear would hear the sound quicker. So if we cycle the thumper, this electromagnetic pulse travels very quickly and hits the sensor and triggers a timing mechanism, and the sound wave hits the sensor much slower at the speed of sound and stops that timing mechanism. So if we go through that again, thumper thumps, the Digiphone starts to record how long it's going to take for the sound to get there. And the closer the sensor is to the fault, the less time it takes for that sequence to take place. So here's what an operator who's walking the cable path might see. To start with, as the operator walks the cable path, he's going to focus on this green line through the center of the display. If that green line shifts left or right, that indicates that he has shifted left or right in relationship to the cable underneath of him. So it's got a rough cable tracer in it, and he's going to want to keep that green line centered up. Then whenever the thumper cycles, he's going to see this coil symbol flash at him, this icon flash, and that's going to happen at the same time that there's an electromagnetic field down on the cable underneath of him. And concurrently with that, he's going to see the acoustic symbol flash. So that's an indication to him that the thumper cycled, and now we have an electromagnetic field and a sound wave on that cable. And depending on where he's positioned at, and in this case, he would see a display that says 7.2, indicating he's got that sensor 7.2 feet away from the fault. So a couple of tips on how the Digiphone works. And again, this webinar is not a training class on the Digiphone. There's quite a bit more to it, but a couple of things that we want to pay attention to. First, when you're using the Digiphone, you want to do it slowly and systematically. You don't want to get in a hurry. It's giving you quite a bit of information, and you want to pay attention to what it's doing. What you don't want to do is you don't want to focus exclusively on the headset or the sound. Yes, it does amplify the sound of the thump. And yes, you can actually pinpoint a fault that way. You can listen your way down to the fault. But we don't want to just listen. The Digiphone is giving us much more information than that. Now here's an example where at position 1, we get a result of 66.9. Now the operator has moved closer to the fault, position 2, and now he gets an indication of 33.8. He moves to position 3, he gets an indication of 12.1. And if he goes past the fault, the indication gets bigger. And the reason that I'm saying indication is the Digiphone can be set to give you an indication in milliseconds. In other words, how much time did it take for the sound to get to you? You can also set it to feet, how many feet away you are, and you can also set it to meters if you're using meters rather than feet. Now, when you're going through this process, Generally, if you were, say, at position 2 and you had the digiphone set to feet, that would indicate you're 33.8 feet away from the fault. When you see numbers roughly around 30 feet, that's where you're going to want to slow down a little bit and use the 2 or 3 thump rule, where now that you've got an indication that you're 30 feet from the fault, you probably want to let the thumper cycle 2 or 3 times and see if that 33 feet doesn't repeat. If it does, you know that it's picking up the fault sound and not some random noise. Okay, so let's switch gears here just a little bit and talk about how you can verify you really did or did not find a fault. We're going to transition back to the arc reflection method a little bit here. And what we want to know is we have some kind of a display. Is it really representative of the fault distance? So in this case, on this particular display right there, that's the fault. Is that a real fault? So let's dive into that a little bit. But before we do, a quick review of the common Tdr reflections. The most common reflection would look like this. This is just looking to the far end of a cable without a fault. Now you'll notice this one looks exactly the same. That's what a broken cable looks like. The radar simply is reflecting off the far end of the cable. It doesn't know whether that's the slid off parked end or whether you're reflecting off a cable where the center conductor is broken, or on unshielded cable where the neutral concentric stops. A less common trace would be this, a short, a downward blip. Usually when you see a short, it's because you've shorted the far end. You've done that deliberately to verify that you're seeing to the far end. A very common reflection would be this, where some of the radar signal has reflected off of a splice as it travels through that splice. And then we can have a cable with a fault. And the radar by itself cannot see that fault. It needs the arc reflection method. We'll circle back to that in a minute. Now over here on the left-hand side, we have the characteristic hookup reflection. This hookup reflection is simply a mismatch between the output resistance of the radar and the cable's impedance. So over on the left-hand side, you always see this bump up. And then everything but the short, there's also somewhere down the cable path, there's a reflection, and it's represented by this bump up. So, you know, I refer to this as the open end, the far end. Another way to think about it, that bump up, that's as far as the radar can see. And then finally, down back to the bottom, the cable with a fault. This is where we use the thumper to create an arc. The radar reflected off the arc. We display it in red to indicate it's a high voltage reflection. And of course, the fault distance is right here where the separation point is. So here we have 2 typical faults. These are typical. They're easy to verify the fault distance, but rather than just blindly accept these fault distances, in the top case, fault at 124 feet, in the bottom picture, a fault at 270. Rather than just accept this, let's verify it visually. And to do that, what we're going to do is we're going to read the radar trace from left to right. And what we're looking for is we're looking for a mirror effect where the red trace should mirror the blue trace from left to right. And then somewhere along the trace, the mirrored traces, the red trace will split or separate downward from the blue trace. And after that separation, the red trace will no longer mirror the blue trace. And we're also looking for this characteristic U or V shape of the fault. And if we measure from left to right out to that separation point, that is where the fault distance is. So this is just the steps that we would go through to verify a typical fault. Now let's look at an example where the radar gave us 2 different fault results for the same fault. And we need to pick out which one of these is real. So let's start by reading from left to right, and let's compare these two results. Does the red trace mirror the blue trace? And I should pause here for just a minute. On your display, this black trace is actually the blue trace. That's just the way we saved it on to the display here. On the actual display of the Smart Thump 25, that black trace is blue. So when I say blue trace, that's the one I'm talking about. But if we look at the top picture, you can see how the red trace does not mirror the black/blue trace. But if we look at the bottom trace, it does mirror. Now, if we look, the red trace is pulled away a bit from the blue trace, but it does mirror it. And so if I have to choose between the fault at 426 in the top picture, excuse me, and the bottom picture with a fault at 300, the bottom picture is the one that's correct. And so this fault is at 300 feet. And I know that because it has the split after the mirror effect. The red trace no longer mirrors, and it also has that characteristic V shape. And if we were going to actually measure out to this manually, we might move the marker just slightly to the left, maybe 290 feet. If you could imagine bringing the two traces together in the lower picture, the fault flag might shift just a little bit to the left. But from a practical point of view, 300 feet, 290 feet, it's not going to make any difference. Now let's review a trace where the automatic software did not tag the fault. It didn't give us a fault distance. I'm reading from left to right. You can clearly see over on the left-hand side where the red trace mirrors through what was probably a reflection off of the splice. Excuse me. And somewhere along the mirror trace, the red trace will split. Now, the mirror effect is not very good in this particular example, but we definitely get this. We can clearly see a very distinct V or U shape, and that's what I'm going to call the fault. I'm quite confident that that's a fault. And because the automatic software didn't put a distance flag on that, I would simply do a simple adjustment. I would put a distance flag right there at that separation spot where on the left-hand side of that V shape, and the software would automatically give me the distance to that fault. Now let's move on to a fault that's significantly more difficult. In this case, we have two results for the same cable, and the first time we took a shot, we got a reflection 93 feet, or a fault distance of 93 feet, but I can't clearly distinguish anything in this. My red trace is full of noise. I can't even see the pole on the fault flag there. It's all disguised over there on the left-hand side. Looking at this, I have absolutely zero confidence that that's a real fault, and I can't verify it. If we go to the bottom picture, it's basically the same thing. Again, it's the software is indicating I have a fault at 88 feet, but I cannot verify that. I can't see a mirror effect. I can't pull out a distinguishable V or U shape. What I can tell from this picture is the operator that was doing this fault locate, he did adjust manually the gain. He lowered the gain, and I can tell that because if you look at the amplitude of the blue trace in the top picture, it's significantly higher than the amplitude in the lower picture. And then I have a third picture. The operator continued to work on it, and this is what he finally wound up with. And this fault is very easy to verify. We have our mirror effect. We have the separation, we have the V shape, and we've lost the mirror effect. And so how did the operator move from this to this? He recognized that he couldn't verify these faults, so he had reason to keep working. And when he got to this, the way he did it was he used a combination of less or more gain and less or more voltage. Those are the two parameters. They're very easy to adjust manually. You can try more or less gain, more or less voltage. And not always, but many times by doing that, you'll get to a fault like this where you can clearly verify that that's a real fault. Okay, so let's finish up with some inconclusive results. Here we have 4 pictures of the same fault. And if we try to apply our rules, it really doesn't fit on picture 1. There's really no mirror effect. You can see the red trace is completely clipped top and bottom. If we go to picture number 2, again, we get a fault indication of 90 feet, but there's no way to verify that. Now, when we go down to picture number 3, we do see some mirror effect. We do see some separation in a very distinct V shape. And if we look at picture 4, it's somewhat similar. We do see some mirror effect. We see a V shape, but we also see the red trace is highly clipped. If I had to choose, I would pick number 3. And what I would do if I was actually working this fault is I would try several more shots at higher or lower voltage, maybe a little less gain, and see if this fault at 1463, if it repeats. If it does, then that would verify that it was real. If it didn't, and I'm just walking this cable path, I might go to that location first and listen there, because that's a strong maybe. Okay, so let's wrap up here with a review of some common Megger systems and fault location accessories. We have a series of integrated radars. You can see the Easy Thump, you can see the Smart Thump. That's basically what we've been talking about here. You can also have radar, standalone radars. There's also a picture of a high voltage bridge here. A high voltage bridge is a completely separate, not separate, but a different method other than arc reflection to get a fault distance. Here we have some non-integrated thumpers. These are usually larger units. You can see how you could utilize a radar with them. On the SFX40 here, there is a radar that's associated with that. We have an SWG thumper. These are larger thumpers, many times used in a wind farm environment. And of course, here we have our Digiphone that we reviewed shortly. Some terminations and cable racks. You know, if you do a truck mount system, you probably will have a cable rack in there of some type. The terminations, this elbow connection up here in the top left-hand corner, that's a very common accessory. It's very useful for connecting a thumper in a pad mount environment through a feed-through. This is a picture of one of our integrated cable test fans. So if we look closely at the picture here on the top left, I can see tucked away in there is the coupler for a PD connection. So this particular van was configured with some fault locating and also some test and diagnostics equipment. And if we look at the side view, you can see stored away in the side door, there's a Digiphone, and I can also see that there's a bridge in there. The example that we're trying to show here is that you can have a completely integrated fault locating system inside of a small compact van. And here's another truck mount system, our Centrix 2. This is the most modern, most powerful test fan system in existence. You can configure this a lot of different ways. Generally, this would have a full-blown fault locating system in it, as well as probably VLF, maybe 10 delta, partially even a partial discharge test and diagnostics. And with that, we've concluded the webinar.
All right, excellent. Thanks a lot. So we'll take a few minutes to answer as many of your questions as possible. If you do have any questions, please submit them now into the Q&A box on the right side of your screen. For those of you that are leaving, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate it if you were to take a couple of minutes to provide your feedback so we can continue to improve upon future webinars. On the survey, there's a field where you can also request a demo or a quote of any Megger products. A copy of this presentation, along with a link to the video recording of the webinar, will be emailed to everyone in 2 business days. You can also view video recordings of previous webinars on our website at us.megger.com/webinars and register for next week's webinar, an insight into insulation resistance testing. The presenter will be Sanket Bular. All right, let's jump into your questions. The first one's going to be for Sergio. Sergio, can smart thumps be used for high voltage cables from the 69 kV to 230 kV range?
Okay. So my answer to this was this depends on the breakdown voltage of your particular fault, and if the breakdown is higher than the smart thump range, a larger unit will be needed. But as to add kind of a side note, if you will, the unit radar and the voltage range is worth a shot using because you don't know the breakdown voltage on these 69 230 kVs. We've had multiple customers who have tried using these ST25s on these higher ranges, and like I said, depending on what it actually breaks down at, if it breaks down earlier than a 25 kV, you can use this unit.
All right, thank you.
Maybe
Henning.
just one brief add-on. The ST25 will go to 30 kV high pot, right? So in general, the question, it's a good thing you'd always check the breakdown voltage, even when you work on a 230 kV cable, because most of the time breakdown voltage, especially on high voltage cables, are fairly low because of the amount of fault current present, which really provides a fairly low breakdown voltage. So for the most part, you can find faults with a medium voltage fault locating system on high voltage transmission cables.
All right, thank you. So your next question, Henning, is could you please provide an example of a voltage that would be used for breakdown tests for a 35 kV cable?
Well, if you have a 35 kV cable, it's the same, basically what we had just talked about. You running a breakdown, when you run a breakdown test, you're not using a defined voltage. You're using the voltage capability of the unit to run it basically all the way up. So when you go in this mode, you would set, let's say, the highest voltage you have on the unit. Let's say in the case of the ST25, you have 30 kV, you punch in 30 kV and you turn it on. If there is a breakdown at, let's say, 17 kV, the unit will stop. If the breakdown is at 28, it will stop at 28. So on a 35 kV cable, especially on an XLP cable, you have 19.9 phase to ground, and that is basically the system voltage. Now, when you have a fault, you have 345 mil of insulation, about 8 millimeter. So the breakdown voltage typically on a 35 kV cable is probably between 8 and 15 kV. So you should always find it with these type of systems that Marshall was talking about. Unless you have this one fault that he also mentioned, if you have a burnt in the clear fault on an aluminum conductor where you need, basically you cannot flash it over because the insulation is burnt back, okay, or the conductor is burnt back. And then you go on the other side and you find it there, okay.
All right. So Sergio, next question's for you. What is the good practice of finding a fault on a multiple branch feeder cable?
Okay, so as stated before, branches require the ability to isolate from some middle point of that said branch. But if you cannot isolate from that branch, what we say is you can try from each end. And if the fault is close enough to your hookup point, meaning let's just say it's a 4 branch, 5 branch, however many branches you decide. And if you cannot isolate from one middle point and look in each direction, you could try from each end. And if the fault, I'm sorry, stumbling over my words. If the fault is close enough to your hookup point, the radar/arc reflection might give you a good enough trace to give you footage, but depends, as stated before, on how close the fault is to your connection point. All radars can only see the cable as one long footage as opposed to footage breakdown at each point. So I'm assuming he understood that already, which is why he's asking about practices. But some middle point that you can isolate from would be the very best method. But if you do not have that ability, try from each end. And I know it'll be a little time consuming, but depending on where that fault is, if it's close to your connection point, your odds have increased with the radar, the arc reflection showing you footages. Hope that answers that. If anybody wants to add, that's fine.
Yeah, maybe I can add a little bit to it. If if you have extensive branching, like in downtown city networks, then typically the TDR method or arc reflection method is not going to be very successful, because you get a lot of attenuation of the radar signal, and the other thing is, even when you get a signal, you have to be able to associate that with a certain point in the circuit. So if you have maybe two, three branches, you can try it, and this method that Sergio was talking about, shooting from each end, will get you there, because the trick is to get the fault in front of the branch. Okay, so you might have to try from a number of different vantage points. But if you had a multi-branch system like in the cities, then you typically use a different method, and that's what we call current chasing. Okay, you're thumping and you're using a galvanometer, and you follow the fault current. You open up the manholes at the branch points, and you see which way the current will go when you're thumping, and that will eventually lead you to the fault. That is the typical method in branch downtown city networks.
All right, thank you. Marshall, next question is for you. How much does thumping damage the cable?
From a practical point of view, probably not at all. You got to remember, many times when you're fault locating, you are working on an aged cable, and you do not want to thump it at any higher voltage or any longer than you have to. But the thumper itself didn't create that damage on that old worn out cable. It was already there. So from a practical point of view, as long as you keep your voltage under control and you're not excessive in the amount of time, you're not out there thumping on a cable for half a day because you're not using the right technique, you're not really too concerned about damaging the cable itself with the thumper.
I think that's a very important comment you made, Marshall, to use the right technique. What starts as a pinhole fault from the actual cable fault, if you don't use the right technique and you just start thumping for half a day, once you dig this fault up and you find it and you dig it up, you might see that that pinhole fault has now developed in a fault that's maybe half an inch big. Where if you would use a arc reflection method, you would maintain that pinhole fault, and it's much easier to find. The larger the fault gets, the harder it is to find it. So there is a good argument to be made. Just don't thump on a fault. Use first the proper TDR arc reflection tool to pre-locate it, and then do the thumping for the pinpointing. And then you will do very little damage or no damage, because the damage will occur at the fault. Okay, so you don't really care about that.
Okay, so our next question is for Henning. Why does the radar sometimes give incorrect fault distances?
Well, the question really is, what is an incorrect fault distance? Okay, I think the person who asked the question means it doesn't meet his expectation of what it should be. Now, sometimes it does not meet the expectation because the fault is not where the person believes it should be, or it could also be that the radar gives him an incorrect distance, like I think Marshall was showing a number of traces, that explained how you verify whether the radar gives you a proper or correct fault distance or not. It's not that the radar works sometimes and doesn't work sometimes. The radar has also, like any other tool, has certain limitations of what it can do and what it not can do. Okay, and so I cannot really give you a answer, you know, how you would get an incorrect radar reading, because it depends how you get to that point. So typically the radar is probably today, aside from the thumper that provides the high voltage, the most important tool in fault locating of medium voltage power cables. And it's a very, very proven tool to do so.
All right, thank you. Our next question is going to be from Marshall. Will the Digiphone work with any brand thumper?
This is an easy question to answer, and yes, it will. The Digiphone, it doesn't matter what brand thumper it is, and Megger sells a lot of these devices with to be used with non-Megger thumpers, and they work great.
All right, thanks. Also for Marshall, is the low voltage pulse radar sent out at the same time as the high voltage signal to detect the fault? Or is there a small delay to allow for the high voltage to reach the fault first?
This is actually a pretty in-depth question, and we didn't talk about this at all in the webinar. The short answer is yes, there is a small delay called trigger delay. If we were to really dive into this question deeply, there are some capabilities that we have today. I did not talk about them, where we can do multiple shots with multiple radar traces with a single thump. The short answer is yes, there is a small delay, a trigger delay, if you will, and that there's a lot of implications to that in whether the radar did or did not successfully identify the fault distance, and there's been some significant improvements in technology, and I'll just leave it at that. Whoever asked that question, they're more than welcome to circle back with us offline, and we can discuss that further.
All right, thank you. So Robert, how's your audio looking? We throw a question over to you. So I've just unmuted you.
I can take that question if you want.
Yeah, we'll throw it over to Henning. So during testing, both cable ends must be connected to the equipment or not. Say, for example, transformer is connected to a motor through the cable.
Well, whenever you test, you can only test from one end of the cable. When you do fault locating or cable testing, you have one end connected to your test equipment, and the other end of the cable must be open, must be isolated. It cannot be connected. So anytime you send high voltage out, you must observe that protocol, because otherwise you might be sending high voltage to take a good example is, for instance, on a low voltage circuit, if you have a meter box connected and you would fault locate and you send 1,000 volts down that cable, you would blow everything up in that house, right? So you must be isolated. The moment you use high voltage, you must use isolation on the far end, and on the front end it's also isolated because you're connecting your equipment to it. Now, there are some tests you can do when you don't use high voltage, when you just use low voltage signals. For instance, the Tdr, if you just use a Tdr, you can have a motor connected, but the motor must be de-energized, obviously, right? So that way you can see, because the motor windings will show you on a Tdr a open circuit, okay? So it is possible, but the basic rule is any high voltage testing or fault locating, you must be disconnected on both sides of the circuit, and on the near end, you typically connect your equipment.
All right, thank you. So, Sergio, is the elbow jumper shielded or does it have a wire ground?
Let's see. So the elbow portion has an unshielded, the elbow itself has an unshielded portion on the lead just before the elbow boot itself. And then if you have the high voltage lead, there will actually be a small lightning bolt laminated picture on that section so that you know in between here and here is unshielded. And then the ground itself is on the high voltage return as well. So it's all intertwined together. Hope that answers that question. Uh-oh.
Oh, we might have lost Marshall. In the meantime, Henning, is it possible to find out fault if there's mixed insulation with more than 5 kilometers and multiple joints?
Yeah, the mixed insulation is not a deterrent from finding a fault. If you have, however, like in many older circuits in the downtown areas, you have XLP and maybe EPR, that's not an issue. But if you have paper cable also involved in it, then paper cable fault locating can be a little different than what Marshall described in his presentation, which was geared around XLP cables. You might need higher voltage and more energy to do fault locating if you have paper cable involved, because inherently you have oil in that paper cable because the paper is impregnated with oil. So in order to get a flash over, oil doesn't flash over as easily as air. So that's why you might need more joules and more voltage to get the initial flash over and to maintain the arc when you do the arc reflection method. There's also another method that we didn't talk about today. It's the surge pulse method, which is a very well-known and long-proven method, which might be on paper cables a little easier to use if the arc reflection does not work. So, but generally, there is no problem doing a mixed cable, and even if you have multiple splices in it, the splices don't affect the capability to fault locate. Now, sometimes you might have a splice in the cable, and depending how splices are made, they are sometimes very difficult if you have a failure directly in the splice body, and you did not bring the concentric neutral in a concentric way around the splice body, then you might have a problem flashing that fault over. So it looks like it's a non-flashing fault. Even when you thumb to ground, you can get it to thumb to ground. So that is what I'm saying. In application where arc reflection, where you need an arc between the center conductor and the neutral is required, if you cannot get that arc, then that method cannot work. So, but it should be typically it's not a problem to find faults on those type circuits.
All right, thanks. Marshall, we get you back?
I'm here.
Yes, he said he's
Beautiful. Okay.
Yep.
So do you ever rerun tests from the other end of the cable if the results are poor?
Absolutely. To go to the other end and to try from the other end is a very common practice. A variety of reasons for this, but that's one of the things to always keep in the back of your mind if you're having a difficult time getting a good result. Before you just turn the thumper on and start walking that line and banging away, you should strongly consider taking your equipment to the other end and try the basic arc reflection technique from the other side. Many times it will give you a better result. And, in simple terms, that's because that fault it may react differently to the energy from one direction versus the other.
All right, thank you.
Maybe to add as a common point is it's always best to try to fault locate from one side. That means you do everything you can do from that one side. If, like Marshall is saying, you cannot get any conclusive results, then you move over to the other side. But try every method you know that you can do from the one side before you move over to the other side, because otherwise you're jumping back and forth, and that is a lot of time, extra time. So exhaust your methods from one side and then go to the other side if you cannot get a clear indication.
All right, thank you. So for multiple insulated cables henning, how do we fix the cable velocity in the software?
Okay, there are a couple things about this topic because it comes up many times. First of all, the TDR method or arc reflection method is a pre-location method. It is not a pinpoint method. That means we don't need to be within 1 inch of the fault, right? If we are typically many times we are on shorter cables, we are maybe within 1 or 2 feet with a TDR. But even if you're not, if you are, let's say, 10 or 20 feet, it's not a big deal because you do pinpointing afterwards. So that's the first thing. So the expectation should be not, because I don't know the velocity, I cannot use the method. That is an incorrect assumption. When I have different velocities, I use a common sense approach. If I have, let's say, a little bit of one type insulation, maybe 10% and 90% of the other, I just go with the number for the 90%. And I know, okay, I'm going to be a little bit off, okay? If I have 50-50, then I can build an average velocity and use that. But always keep in mind, whenever you average or you calculate velocities, the fault, depending where the fault is actually located, might have an impact on that distance. So one way to eliminate this is the three-stake method, where you go from one side, you use a fixed velocity, you go from the other side, use the same velocity, and when you get a distance between these 2 points, which normally should match if the velocity would be correct. If it doesn't match, then you basically use that distance and divide it by the ratio of the two distances, and you get the third location. So there are some ways to do it, but typically it's not a big deal, because the most important thing is it's a pre-location method, and you normally get very close enough to the fault to be able to pinpoint it.
All right, thank you. So Marshall, the next question is for you. How many joules do I need to thump correctly with a PILC tripolar cable fault?
The joules is a result of two things, the voltage and the capacitance. Now, the capacitance that you're working with is fixed by the particular thumper that you've chosen to use, and of course the voltage is adjustable. So we don't, and I may not understand this question correctly, but what we're doing is we're going to do a breakdown test that tells us how much voltage we need to use. And of course, we can control the voltage output of our thumper. So the joules is going to be a result of the thumper we've chosen to use, because it has a set of capacitors in it, and the voltage level. Now, whether it's PLC cable or any other cable, the general rule is, once we've done that breakdown test, we want to use the lowest voltage range available to us. That will provide the largest amount of capacitance, and that's going to give us the largest joule number. And then I guess the question was specifically about PILC cable. In general, you do use larger, heavier duty thumpers with larger capacitors, if you will, because you do, as Henning mentioned earlier, with the laminated insulated cable, the oil itself does not flash over nearly as easily as an air gap. So on those type of PILC cables, you are probably going to be using a bigger thumper. But the rule would stay the same. With that bigger thumper, you want to use the lowest voltage range that you can get away with, because that's going to give you the most joules at the lowest voltage level.
Maybe one comment on this, because it's not totally clear from the question. If it says tripolar cable, so it's probably a segmented cable, has 3 segments, 3 phases in it. The question is it a belted cable or not a belted cable? If it's a belted cable, where you have only one common neutral for all 3 phases, you might also want to make sure you're testing face to face and not only face to lead sheath, because if you have a face to face fault, you wouldn't find it. And the other thing is, typically on paper cable, most paper cables are used at 13.8 or 15 kV. So if you have a system, the system should have at least a 30 kV high pot capability. So you get initial flashover, and it should have, like Marshall said, enough joules to sustain the arc, so you can get a good thump. Okay.
All right, Henning, so our next question for you is, how do you locate a fault on an unarmored cable?
Now, again, that question is a little, it's not totally clear. Armor is typically a purely mechanical protection that's applied to a low voltage or medium voltage cable, or to a high voltage cable, which is basically steel wires that are applied on the very outside of the cable, and then typically covered with another jacket. So that has not much to do with the fault locating, unless you have a low voltage cable. Low voltage cable in Europe and typically in Europe are not armored. So you have not a shield and you don't have an armor. So basically you do fault locating face to ground. And when you have a low voltage cable that has an armor, it can serve, so to speak, as a shield. So I can now flash over to that armor, and I have a ground again. So I can use some of the fault locating methods for medium voltage cable, also an armored low voltage cable. When I have a armored medium voltage cable or high voltage cable, and my fault is between the center conductor and the metallic shield, that armor doesn't have any influence on it.
All right. I think we have time for one last question. That's going to be from Marshall. Is it possible to detect 2 faults on the same cable?
Boy, I could tell war stories about this one. Yes, you can, but think it through. You have 2 faults, 2 paths to ground. When you start to apply high voltage, in general terms, that voltage is going to seek the path of least resistance to ground. So what happens when you have 2 faults, assuming that they have different resistances, is you'll find the lowest resistance fault first. And then, of course, you don't know unless if you perhaps you repair that fault, and then you do a quick verification, high pot test to make sure there's not a second fault. You won't know that second fault is there until you try to re-energize. So you can find 2 faults, but you have to find the first one, fix it, and then verify that there's not a second fault. And that's where the war stories come in, because generally you're not expecting 2 faults. So if you don't do a quick withstand test before you re-energize, you may not know that second fault is there till you closed in.
You know, there are a couple rules you can apply. If you have two faults and one of them is a dead short, you must always repair the dead short before you can find any second fault. If you have a two-fault scenario, let's say with a pinhole and a burnt in the clear conductor, then you might find the open point from the burnt in the clear, and you find the pinhole fault, because the burnt in the clear will not flash over, where the pinhole will flash over, following the principle that Marshall was explaining, following the path of least resistance. So it all depends where these faults are relative to each other, and from which side you're looking at it, and what the nature of the faults is. There are situations where you can find two faults, but typically you cannot.
All right. It looks like that's all the time we have for questions. We apologize if we did not get to your question today, but we will be following up with you offline in the following weeks. Thank you all for attending. If you would please remember to answer the survey. This survey will also include a field for you to request a demo or quote if you're interested. But thank you all again for attending, and I hope you have a great week.